Now, if we can do definite integrals with trigonometric substitution, that means that a lot of the applications that we learned in chapters 6 and 7 can rear their ugly heads again. So we're going to look at one of the applications we considered back then, which is arc length. Arc length has this formula, and then we can use that now. So let's see here. If I look at my particular problem right here, I notice that the derivative of f of x, f prime of x, which I need, of course, for the arc length formula right there, would be 1/2 times 2x, right? Because you bring the power down. In other words, it's just x. So then when I want the arc length, I'm just thinking about preparing myself. I know I'm going to need trig sub, so I'm just going to start by divvying up my paper. It's not quite half and half, but it's getting there. All right, so arc length would be equal to the integral from, all right, now they want us to go from a to b, so 0 to 1, square root 1 plus f prime of x, which is x, squared dx. I mean, it seems so simple. It seems so easy. However, that's not an integral we know how to do until trig substitution, because a squared plus x squared is this form in the middle right here, right there. So we're going to be using the tangent of theta is equal to x over a. That's going to be our trig sub. So the tangent of theta is x over, now a for us is 1. So you can see it right there, right? If a squared is 1, then a is 1, right? So that means that we're going to be using tangent of theta is x over 1. There's our trig sub. All right, and then we can build our triangle. Here's theta. Tangent is opposite over adjacent. So this is x, this is 1, and this is actually a really easy one. X squared plus 1 squared is equal to hypotenuse squared. So the hypotenuse over here would be the square root of x squared plus 1. Pretty easy over there. All right, now let's think about the pieces that we usually need. We need x, so x would be equal to the tangent of theta, right, because a is 1, so that's easy. Then we need dx. Derivative of tangent is secant squared theta d theta. So this will be the first piece of substitution we make, and then this will be the second piece, as per usual. Then, of course, theta would be equal to the arctangent of x. Technically x over 1. Now, why do I need to know that? Well, because I'm going to have to do some substitutions here. So when I take my integral, and let's use it here. I can't put 0 and 1 because I won't be working with x anymore. It'll be the square root of 1 plus, and then where there was an x will become tangent of theta. So it'll be square root of 1 plus tangent squared theta. And then I'll multiply it by secant squared theta d theta. But notice that d theta. So there's the x, there's the dx. But if I notice that d theta, that means that I can no longer use 0 and 1. I have to come up with new numbers to be my definite integral numbers. All right, so when x was equal to 0, theta is the arctangent of 0. So I would need an angle on the unit circle. There's my unit circle. Everybody loves it. I need an angle on that circle that has a tangent that is 0. So I need its sine to be 0, but its cosine to be 1. That way, when I divide, I won't get infinity or something weird, undefined. I will get 0. So 0 divided by 1 is 0. So this angle actually is 0. Lovely. Now what about when x was equal to 1? Then theta would be equal to the arctangent of 1. So I would need an angle that sine over cosine would be the same value. And that's right here. Pi over 4 is 1 over the square root of 2, 1 over the square root of 2. So if I take the sine over the cosine, I will get 1, right? Sine over cosine is 1, and therefore the angle is pi over 4. Okay, so these are my new numbers, my new limits of integration. So this is going to be from 0, and this is going to be pi over 4 up here. Okay, so now, I don't know about you, but I'm thinking Pythagorean identity, right? Because 1 plus tangent squared, that's Pythagorean identity. That's secant squared. So let's see here. This is the integral from 0 to pi over 4 of the square root of secant squared of theta, right, with Pythagorean identity. And then I already have a secant squared theta sitting outside, and then I have my d theta. Okay, secant, the square root of secant squared is secant, and secant times secant squared will be secant cubed. So this will be secant cubed theta d theta from 0 to pi over 4. And I will yet again use a reduction formula, right? We have a reduction formula. That's what we're going to use at this point, which is right here. So secant cubed, so n for me is 3. So I'm going to use this formula and write it all out. So let me see here. This is equal to secant to the n minus 2. There's kind of no way for me to show this 2 at the same time. So secant to the 3 take away 2 is 1. So secant times tangent over 2. So secant theta tangent theta over 2. And that would be taken from 0 to pi over 4. Right? Because there's no more integral on that piece. Plus, and then n minus 2 over n minus 1. So n minus 2 is 1, right? Because 3 take away 2 is 1. 3 take away 1 is 2. So that's 1/2. So minus a half, or plus a half, excuse me, plus a half integral. And then secant to the n minus 1, which would be secant to the 1 of x, secant of x, I guess I should say, secant of x dx, or secant of theta. Sorry, the formula uses x, but of course for our problem we're using theta. And then again, this would be from 0 to pi over 4. Okay, well the secant of theta is, or the integral of secant of theta is on our sheet. It's right here. It's the natural log of the absolute value of secant of theta plus tangent of theta. Okay, so we used a reduction formula to get here. Formula. There we go. And this was number 4. And now we're going to use number 12 on the quick sheet. I'm not going to bother putting in pi over 4 and 0 until this is all over, because I want to try to make it so that's one thing, and it will be actually. So, and there's a half. Do you see how there's a half in both of them? So I'm just going to factor that out. So that leaves me secant of theta, tangent of theta, plus, I factored that half out, and the integral of secant is the natural log of secant of theta plus tangent of theta. And all of that is from 0 to pi over 4. Amazing, isn't it? Okay, so now we just need to put the work in, right, and do this. So luckily for us, one of this is actually very easy, because if I have a half in here, the secant of pi over 4, right, so I want the secant of pi over 4, the tangent of pi over 4, plus the natural log of the absolute value of the secant of pi over 4 plus the tangent of pi over 4. Oop, left no room there. That's all the pi over 4 bit. However, I'm not really worried about the other bit. Let me show you why. So this is all pi over 4, pi over 4, pi over 4. Right? What about 0? Well, we just said the tangent of 0 is 0, right? Tangent of 0 is 0. So let me put that in over here. So note, the tangent of 0 is 0. And then for the record, the secant of 0 is 1 over the cosine. So that's 1 over 1, which is 1. So this is 1, this is 0, right? And then this is 1, and that's 0. So for this back one, what's going to end up happening is that it's all going to be 0, right? There's not going to be anything there, right? So this term is 0 because the tangent of 0 is 0. This term is 0 because the natural log of 1 is 0. So that whole thing is 0, which makes things a lot easier, as I said. Let's go over and figure out the secant of pi over 4 and the tangent of pi over 4. So, well, we actually know the tangent of pi over 4. The tangent of pi over 4 is 1. I mean, that's what that means. The secant of pi over 4 is 1 divided by the cosine. So if you look at pi over 4, the cosine is 1 over the square root of 2. So it's 1 over the square root of 2. In other words, it's the square root of 2. So that's the secant. So that means that over here we'd have a half, and then it's square root of 2 times 1 plus the natural log of the square root of 2 plus 1. Oh, I forgot my plus. I technically don't need absolute values anymore because that is positive, so we're good. And that is the answer, which is of course terrible. So we should come up with some kind of decimal approximation to check that we did this right. And that is what Desmos is useful for. So here I have the original integral. I mean, it's so simple seeming. It seems like it's so easy, but it actually is quite tricky because you have to do it with trig substitution. You have no choice. So here's the integral after I did the trig substitution from 0 to pi over 4, and you can see they're the same value. And then there's my end result. So I can check that what I said was true is true, and that it is 1.1478. And so that's what I will put as my decimal approximation. Now, to us in units, if they said, just for example, if x is in meters, right? Assume. As a matter of fact, you can assume x and y are in meters, right? Y being your f of x. So if x and y are in meters, then your answer for arc length would also be in meters.